Okay, so in this problem, we're going from an initial state with n on 4 particles here and 3n on 4 particles here to some final state with n on 2 particles here and n on 2 particles here, and we're asked to calculate the change in entropy, which will be the final entropy minus the initial entropy. Now, to cheat a little bit, we've already calculated the entropy of this final state. We just did it in the video you've just watched. So we know that the entropy of the final state is equal to Kn log 2. So that leaves us with just needing to calculate the entropy of this initial state. Okay, so in order to do that, the entropy of the initial state, we'll use Boltzmann's expression, which is K log Wi, the multiplicity of configurations for the initial state. And the multiplicity of configurations for the initial state are n factorial over n on 4 factorial times 3n on 4 factorial. Okay, so we have S initial is equal to K log n factorial over n on 4 factorial times 3n on 4 factorial. Now we'll use our log rules to expand this out. So we've got n factorial divided by n on 4 factorial divided by 3n on 4 factorial. So this is equal to k, we'll put k out the front, and we've got log of n factorial minus log of n on 4 factorial minus log of 3n on 4 factorial. And now we're going to use Stirling's expression, which tells us that log of n factorial is approximately n log n minus n, in order to simplify this expression. So that tells us that the initial entropy is equal to k out the front, and then this one here is n log n minus n. This one here, we've now got minus log n on 4 factorial. So that's minus, this n is now n on 4 log of n on 4. And now we've got minus minus, so that's plus n on 4. And then here we've got minus 3n on 4 log 3n on 4 plus 3n on 4. Okay, so we've got minus n plus n on 4 plus 3n on 4. This one plus this one is equal to n, so these cancel each other out. So those ones cancel, and we have that this is equal to, let's also pull this n out the front just to keep everything as simple as possible. So we've got kn log n minus log of, well, 1/4 log of n on 4 minus 3/4 log of 3n on 4. Okay, so now we want to put our logs back together. We'll start by getting rid of these factors out the front. So we can do that by raising these things to the power. So this is equal to kn log n minus log of n on 4 to the power of 1/4 minus log 3n on 4 to the power of 3/4. And now we'll multiply and divide these. So we've got k on n times log, this is n divided by n on 4 to the 1/4 times 3n on 4 to the 3/4. Okay, so this is kn log. Now at the top we've just got n. Now here we've got n to the 1/4 times n to the 3/4 times 3 to the 3/4 over 4 to the 1/4 times 4 to the 3/4. Okay, so 4 to the 1/4 times 4 to the 3/4, that's just 4. And we're dividing that on the denominator, so we can actually move it up the top. And n to the 1/4 times n to the 3/4, this is just equal to n. So this cancels with that. So we have Kn log, this comes up the top, that's 4, and this is over 3 to the 3/4. Okay, so we've now got an expression for our initial entropy, and we've got an expression for our final entropy. So the change in entropy is equal to Kn log 2 minus Kn log 4 over 3 to the 3/4. So this is equal to Kn log 2 divided by 4 times 3 over 3/4. Just putting these log functions together, we divide this by this. And so this is equal to Kn log 3 to the 3/4 over 2. Okay, now 3 to the power of 3/4 is equal to approximately 2.28. So the point is it's bigger than 2. So this is positive, because we were asked if the sign of this was what we expected. Well, this is going from a more ordered state to a less ordered state. So we would expect the entropy to increase in this case. I mean, this is going to happen naturally in an isothermal free expansion. As it expands out to fill the room, which is this final state, it'll pass through this state and keep on going. So we would expect that this entropy is increasing as we're seeing here.